Hey kiddos, happy lesson number 3. Today we're going to break the lesson into a couple pieces. This video is going to be lesson 3A, and then I'll take a look at lesson 3B. All right, so here are today's goals. We're going to introduce the law of introduce Newton's universal law of gravitation and practice using it to problem solve. We're going to introduce gravitational field strength and calculate the speed of orbiting objects. Now, this is our last unit in mechanics. Actually, it's not mechanics. It's a new unit. It's topic 6 called fields. So it'll be our topic that bridges the gap between mechanics and electricity and circuits. All right, we're going to talk about gravitational fields first, and then we'll talk about electric fields. So something important to note as we're doing this lesson is it'll be nice to have the inner cover of your textbook ready to go. So if you log into Wiley Plus and you see this screen here, go ahead and click to get into the screen. And I don't know if your landing page looks like mine, but go to read, study, and practice. And we're going to access the textbook. There are all these chapters, but if you scroll all the way down to the bottom, click on appendices, and you want this front paper. Okay, so front matter, back matter, I don't really know what's going on, but you want the BM front paper, and that'll give you all of the constants that are given to you in the front cover of the textbook. And that'll be really important because we've got stuff like the universal gravitation constant, which we'll need for today. And then there's some stuff like there's the Earth. You see that right there? Earth, the Earth's mass, and its radius, and its average distance from the sun. The formatting here is kind of funny. But then you've got the moon's mass, radius, and average distance from the Earth, and the sun's mass and radius. Those will be really important for this lesson. Okay? All right. So let's get going. So if you have not yet done so, a good thing to do this week, just to get a little more historical perspective, is to watch that Cosmos that I posted over our spring break. Okay. This was one of the things where back before Newton came up with his universal law of gravitation, people didn't really use science as a predictive tool, right? That Cosmos shows comets and stuff being omens of doom, right? Not just regular things that happen. And so this is really the transition between things being messages from the gods or God and just a physical phenomena that can be repeated. So what Newton came up with, and this was pretty crazy, is he came up with a relationship that said the force exerted by gravity between two objects is proportional to the product of the two masses and divided by how far they're separated, center to center squared. Okay. This was something that he came up with observationally, and he proposed that gravity is a force that acts between any two masses. And this was, again, it was pretty revolutionary. One of his biggest failures he felt in his life was that he was able to make predictions using his equation, and he knew that it was true, but he didn't know why this was true. And we actually didn't know why gravity worked until 2016 when a place called LIGO in Hanford, Washington, and there's another observatory in Livingston, Louisiana, actually confirmed the mechanism for gravity being that objects make a dip in space-time and send out gravitational waves as they're accelerating through space. So we'll talk about that a little bit later. But before Newton came up with this idea, heck, there were so many crazy ideas about what gravity was. There is a particle called a graviton that some scientists thought was exchanged between masses, and that's how gravity worked. Back in like the Greek times, people thought that objects were attracted to the material that they came from. So like rocks were attracted back to Earth. Birds were attracted to the sky because they were made of air. And so there are a lot of crazy ideas. A way to write this fully is Einstein said these two values weren't proportional, but there's an additional constant that makes the two values equal. Okay, and so he uses this capital G as a proportionality constant. Okay, and so this is Newton's universal law of gravitation. And it says that these two masses are any two masses in kilograms, right? And this R is the separation of the masses. And it's not the separation of their surfaces, it's center to center. Okay, in meters. All right, so when you look at that resource that I showed you in your textbook that gives you distances and radii, the distance r here between any two planets, you want to take their radius, right? The distance that separates their two surfaces plus the radius of the other planet. Okay, and this entire distance will give you what we're calling R, right here, right? That distance separating center to center. Okay. Sometimes in other resources, they'll use a lowercase d instead of r. A common misconception is that r is radius, and that's not true. Okay, so let's take a look at what this big G is. So capital G is called the universal gravitation constant. Okay, and it's abbreviated as a capital G. Okay, so we can't just say G and think it's acceleration due to gravity anymore. Capital G, specifically in physics, is this universal gravitation constant, and it's equal to 6.67 times 10 to the minus 11. You can remember it because it kind of rhymes, right? 6.67 times 10 to the minus 11. And as units don't super matter, it's newtons times meters squared per kilogram squared. Okay, now I'm going to go ahead and box this. This is the official version of Newton's universal law of gravitation, and this is Newton's universal gravity constant. This constant is tiny, right? Times 10 to the minus 11 is really super small. So if you were to put in like two people, maybe they have masses of 50 kilograms each, right? 50 kilograms times 50 kilograms is 2,500, and maybe they're separated by a meter, so divided by 1, right? So 2,500 divided by 1, and then 2,500 divided by something times 10 to the minus 11. How big would the gravitational force be between two people? Super, super tiny, right? So gravity really only works when you're talking about objects close to really big masses, like a planetary scale. It would be super inconvenient if you were significantly gravitationally attracted to small objects or other people, right? You're gravitationally attracted to anything, okay? But it's not significant and it doesn't impact our lives, okay? Except that we're attracted to the Earth. Okay. So here is just a conceptual example. So it's common for masses to be written as mass 1 and mass 2. I actually want to go back here and write this equation in another way that I actually think is more convenient. Fg equals big G capital M lowercase m over r squared. This is the way that actually I prefer to write this equation, because typically you're dealing with a big mass, right? Capital M mass, like a planet or something, and then a smaller mass that's orbiting around that bigger mass. So we could talk about the Earth and a person or a satellite. Okay, the Earth would be capital M and the satellite would be lowercase m. Or we could talk about the moon orbiting the Earth. So capital M would be the Earth and the moon would be lowercase m. And so it's a little more like visually informative when you're writing it that way. Okay, so here's a conceptual question that I would like you to consider. And you probably are going to want to pause. And I want you to say, okay, so if you've got two masses called M1 and M2, right? This distance apart, they exert a force that we're calling F, right? What if mass 1 doubled the size? How would that change the gravitational force between them if they maintain the same distance? Right, same question, what if you doubled mass 2 instead? How would that change the gravitational force between them? And then what if you doubled them both? Okay. Now, over here, what if mass 1 and mass 2, a certain distance d apart, exerted a force F on each other? Okay, what if you doubled their distance apart? How would that change the force? And what if you halved their distance apart? So take a moment, pause the video, and then see what you come up with.